A laser gives off pulses of blue light with a wavelength of 450 nanometers. If a single pulse from the laser has a total energy of 12 millijoules, how many photons are in the pulse? So there's two equations that are on the datasheet that are going to be helpful for solving this problem. The first one is E equals H nu. And so the E right here, this is just for one photon. Sometimes if you have photons either emitted or absorbed, that'll just be a single photon instance where you can use this equation. But we want to find the number of photons in a pulse. So there's obviously going to be many. And so a really similar equation for when you're dealing with more than one photon is E equals N, where N is the number of photons, H nu. And then the second one that'll be helpful is C equals lambda nu. And we're going to rearrange this one so we can combine them. So we're going to solve for nu and then plug it into this equation up here. So nu equals C over lambda if you just divide that over. And then we're just going to plug this in for nu up here. So the equation that we're going to use to solve this problem is E equals NHC over lambda, where E is the energy of all the photons, N is the number of photons, H is Planck's constant, C is the speed of light, which is also a constant, and lambda is wavelength. So now we can just plug in what we know into this equation. So you need to recognize that energy always has to be in joules, and in this problem they gave it to us in millijoules. So the first thing you want to do is just convert 12 millijoules to joules. And milli always means 1,000, so there's 1,000 millijoules in 1 joule. So our energy is going to be 1.2 times 10 to the negative second joules. So we'll just plug that in for E. And then set that equal to everything else. So N is what we're solving for. H is the constant that is given on the data sheet, so you don't need to memorize it or anything. And that is 6.63 times 10 to the negative 34 joules per second. And then C is also on the data table, which C is 3 times 10 to the 8th meters per second to the negative 1. And then our lambda is also given in the problem, which is 450 nanometers, but we need it to be in meters. So nano means 9, so there is 450 times 10 to the negative 9th meters of wavelength. So now we can just solve for n, just multiply this over, divide by everything next to the n, and n comes out to be 2.7 times 10 to the 16th photons. And so our units cancel out to meters, seconds, we have joules on both sides. So we're left with a unitless number, so we know that n has to be in photons because the energy is the number per the number of photons. So this is our answer to the problem. And I just want to make note that this is a super useful equation that you can use with almost any energy photon problem. If you're just dealing with one photon that's either like emitted or absorbed, you can just use E equals hc over lambda. Or if you're dealing with something like this problem with a pulse with a lot of photons, you can pretty much always use one of these two equations and they'll work for almost any energy photon problem.